webinar, and I wanted to thank you all. I mean, our team wants to thank you for participating today. And in fact, what we wanted to do is to not just have a traditional webinar, but primarily have very brief slides, say a few only, from the members of our team. So just to be able to initiate a discussion about the need for a national network, specifically of infrastructure for emerging. I'm Linda Katehi, and I'm a faculty member at Texas A&M in the electrical engineering department. My area is in RF front-ends historically. I have been introduced to emerging memories about 7 years ago as I was trying to work on intelligence for electronics. And since then, I connected with a lot of experts in this area. And I would like to discuss in the next few slides, after I speak a little bit about the agenda of the webinar, on why we got together and why we want also to discuss with you the future of the research in emerging memories, and in fact, the need for an infrastructure. So I will expand this to make it a little better. And then from here, I will use the arrows. So I will be the moderator today, and we are going to have 4 speakers: Joshua Young, Qiangfei Xia, Cosme Lin, and Swin.
Hello, can you hear me?
Yes, we can hear you. And I will introduce them as they will come along to talk, just present a couple of transparencies to talk about the infrastructure rather. I just wanted to say why we got together to look at what's available, especially for me as a newcomer to this area 7 years ago when I tried to think of how to introduce intelligence in RF front-ends, specifically for edge, I would say processing rather than computing. I realized that a lot of the facilities were not available. If anybody wants to like people like me, like a faculty member who wants to do some interesting designs in circuits and systems. And when in the effort to try to have access to this, I spoke with Joshua and Qiangfei and of course Cosme and Suin. But also I want to show you here that our country does not have its fair share in terms of memory research in general, or development or technology. And that, in fact, gets worse as we are looking at not just design, but infrastructure, fabrication, or manufacturing of the appropriate materials that are needed, wafer fabrication and packaging and so forth. And all of these are important, obviously, in the fundamental efforts to develop memories and memory chips. So from there, I'm going to this one. That is what we have put together. In fact, the 5 of us, some time ago, I apologize for this one. Some time ago got together to submit a pre-proposal to NSF mid-scale infrastructure program. And specifically was on that recognition that there is very little available for the average researcher, average in terms of, you know, in the group of researchers, but of course, it does not talk about the quality of the person, obviously, but I'm talking about individuals who want to get into this field, they have an interest, and they do not find infrastructure available to be able to help in the research and development. And so we submitted a pre-proposal, and NSF invited us to submit a major proposal. So that's how we started. And that it shows, as a matter of fact, down here in the emerging memories of what we are focusing on in terms of research and development, and where we think there is a need for an infrastructure that is going to be available. Because obviously, as you will hear from the other presenters, there are facilities within government labs, company labs, industry labs, but not necessarily available to researchers who would like to pursue work in this area. So with that, I would like to start with Joshua Young. Joshua is very well known in the area of emerging memory materials and devices and circuits, obviously. And he is a faculty member, a professor at the University of Southern California. And with that, I will invite Joshua to start. And Joshua, you need to unmute yourself.
Yes, thank you, Linda. Thanks everyone. When you see infrastructure for memory, that's not something new, right? And we know there are great facility in the national labs, in industry, in university. And so why do we need this? And what new here? Why it's necessary? Here, actually, the major reasons are listed here. For eMERGE, we are focusing on memory for computing, for processing, rather than the traditional memory. Those are actually, the memory for computing, for processing actually have different performance requirements than the traditional memory. I will talk about a little bit about that later. So the second thing is, even though we have a lot of tools out there scattered around, the country, they're not necessarily accessible to everyone. And what we're going to do here in this center, so it will be something available for every qualified researchers in the country. And third thing is, we're not just to have some scattered tools, rather we're trying to make it a one-stop shop for memory research and development, with not only the equipment, the instrument, and also the related expertise. Hopefully in this center, it's a networked center, and we can provide those. And the last but not least is we're university based centers. One of the major goal is really for workforce training in this field for the needs of industry and the national labs and the university in the future in this field. And next, please. So, like I said, memory for processing and computing, they pose different challenges. As the radar plot on the left shows, this is just use one example, RAM as example, say, for different applications, for memory, for logic. As you can see from the plot, the memory requirements for computing is different from the large scale freestanding memory. For those traditional requirements, you need a really high density of really high memory density, and you need a great selector. Just a transistor selector may not be sufficient to get you the density. And you need to have a really low bit error rate, for traditional memory. But for computing, you care something else. And the DRAM density is sufficient. Then transistor can be a good selector there already. And you care a lot more resistance levels, and each resistance level needed to be really stable for inference application, so on and so forth. So that is one of the reasons we needed to shift the focus a little bit, if we want to use the memory for new applications. And the figure on the right is, we have a different type of emerging memory for such purpose, the RAM, magnetic, phase change, ferroelectric, so on and so forth. They are at a different maturity level, and they are also based on different physical phenomena, mechanism. That's why they have intrinsically different advantage and disadvantages. Those will be studied with the infrastructure we propose. One thing very common about all those type of different memories is this. They are pretty much all based on very thin films, a couple of nanometer. And we're talking about very small devices, tens of nanometer. So this makes the materials in the device very, very sensitive to contaminations, by air, by moisture, and also by the process chemicals, the process parameters. So that's why very often we get weird result, and we don't know what's going on, and we get very controversial conclusions. So that's why in this center, next place, we propose something. We needed to have a tool set that can give us quick and conclusive answers when we see weird behavior, in such a device. We needed to make the device, characterize them, and in a very well-controlled condition. And it's an in situ cluster tool. You're going to see this is a common thing, for most of the tools we proposed here. It's needed to be in situ. In this case, it is ultra high vacuum, connecting every tool together. This actually is an image I got from a tool in Europe. And this is in the leading lab in Europe. As you can see here, you can deposit your film by sputtering, evaporation, PLD, in situ, and they are connected together. Then at each layer, you can transfer the film to a different characterization chamber to look at the electronic structure, chemical position, so on and so forth. And you can imagine this is a very useful tool. And also, I know recently there is a similar tool built in China by Tsinghua University. And I'm not aware of such size of a cluster tool in the US. And we're going to build something like this, and we're going to do it even better. Because in this tool, as you're probably aware, there is a key piece missing, which is the device fabrication. Next slide, please. So not only you deposit the film and you characterize them, you better make your device also in ultra high vacuum to get a conclusive answer. I know this is not for industry. Of course, for industry, you're not going to do that. But in order to understand what's going on, to solve some mystery we observed, this will be very helpful. And so you make the device in ultra high vacuum. Normally it's hard, but for memory, fortunately, the device structure usually is crossbar. It is doable. As you see in the center, that is a figure of in situ device fabrication we developed with a leading vendor in this field. And basically, it's in situ shadow mask allow us to deposit film and make the device in ultra high vacuum crossbar structure with smaller than 5 micrometer by 5 micrometer. We're going to integrate those key components to this type of in situ tools. In this example, the tool is for inorganic dielectric memory. In fact, we are going to have other in situ cluster tool for organic type of materials and memory, and for low dimensional type of materials and memory, which will be talked by Qiangfei and Cosme.
Very
next.
good. Thank you, Joshua. So that's next, Professor Qiangfei from University of Massachusetts, also an expert in
okay.
research.
Thank you, Linda.
Thank you. Go ahead, Qiangfei.
Okay, so we understand for a lot of devices we are using nowadays is based on the, say, transition metal oxide. But on the other hand, we have a lot of demands in wearable or flexible electronics. So leveraging the a very strong partner program at the UMass, we also propose Glovebox cluster tool for organic memory devices. So this is just some example of the equipment we want to put together. On the left, you see a cluster tool for you can do the evaporation and also a sputtering. In the center, there is a Glovebox, which we are going to be putting the thin film deposition, such as the spin coating and also inkjet printing capability inside. And in addition, we're also going to do the materials characterization and more important, the device characterization inside of the Glovebox. So you see in the Glovebox, there is a probe station with a microscope inside. So this measurement system is going to be connected with typical measurement apparatus such as the semiconductor parameter analyzer, oscilloscope, waveform generator, et cetera. So all this is going to be interconnected in the device fabrication and measurement. They are going to be performed inside of the Glovebox with the protected environment. So and also this substrate we are thinking is also of course for the development stage we can use traditional substrates such as silicon oxide wafers. But down the road, we also want to use flexible substrates such as the plastics. And after this proof of concept is done, we want to move one step further. Next slide, please, Linda. We have an infrastructure here at UMass as the row-to-row fabrication facility here. This is actually about $40 million investment from the Commonwealth of Massachusetts. This is an existing system here. So our idea is once the polymer memory devices is developed, we want to move to the row-to-row for kind of manufacturing prototyping. This is just the two examples of the equipment we have. We actually have, I'll call it a pilot line with evaporation, sputtering, metrology, and including a lot of patterning tools such as imprint in the row-to-row line. So that's is the development idea is going from the device study to the pilot manufacturing. I believe that's what I have for now.
Perfect, thank you. So the next one is Cosme Lin. Cosme is a faculty member at, well, he's an incoming faculty member at Texas A&M coming from TSMC. And he will talk about this now tool. Thank you, Cosme.
Yeah, thank you, Linda. So the third piece of cluster tool we are going to offer is focused on the fabrication, characterization of low-dimensional material-based memory devices. So this is in complementary to the first tool we just talked about. So low-dimensional materials has a very interesting transport properties. And because of their low dimensionality and many quantum effect, it can host many new types of memory devices, which can give us out-of-box device performance. And it can also be easily monolithically integrated to the existing silicon platform. So we can implement a 3D monolithic multifunctional system relatively easily. And here we are proposing interconnected Glovebox system that can host all different kinds of studies around these materials. So the materials we are focused on are low-dimensional materials like 0D quantum dots, 1D carbon nanotubes, nanowires, and different types of 3D layered materials. So they are atomically thin or atomically small. So they are even more susceptible to any environment interpretation and chemical contamination. So we do want, the ideal case is to conduct all the necessary environment within the same inert platform. Then we worked with the vendor and designed this connected Globebox system. On the left are the design, and at the bottom right is an example image from the vendor. So this is how the system is going to work. And the Globebox system offers more flexibility than the UHV system because we can use gloves to reach into the different tools. So we can we can design the experiments with more flexibility. And we want to incorporate all the required tools to conduct the research and development. On the right, I listed the two categories of tool sets. The first category are on everything about material processing and nanofabrication. This tool set includes a Globebox dedicated for different types of wet processing, a dry transfer station for the assembly of low-dimensional material heterostructures, and also for the alignment of a shadow mask if you want to do patterning. And then an ALD tool for the deposition of conformal nanometer thick dielectric materials, a UHV sputtering and evaporation tool for the deposition of high quality metallic and dielectric materials, and then a customized CVD system for any required annealing, CVD, or other chemical processes around the low dimensional materials. Then we also offer different types of material categorization and device measurement tools within the Globebox. For example, optical microscope, so we can inspect the device or materials quickly. Raman to figure out the chemical compositions and the crystal structure of the materials. And we're also going to integrate a high-end AFM tool to categorize all different types of surface physics, including magnetic force microscopy, electrostatic force microscopy, Kelvin probe, conductive AFM. So using this, we can categorize the memory-related properties in the atomic level. We're also going to include a compact probe station within the Globebox, so we can categorize the memory characteristics easily, all within the same system.
Very good, thank you. So the next one, we'll ask Suyin Yi, who is also a faculty member here at Texas A&M, to talk about some of the interesting work or important work in dynamics that needs to be made when it comes to memories, and then the metrology system behind that study that is needed. Thank you, Suyin. Go ahead.
Thank you. Yeah, I'm Suyin Yi. Before going into the details of the slide, let me talk about the motivation why we need these dynamics in memories. Historically, the memory industries, memory semiconductors are typically considered as a medium to store the digital information. So such as SRAMs, DRAMs, flash memories. The industry people, and also we were not very interested in the dynamics, but just we were focused on the end state, just the zeros or ones. But when it comes to analog computing and analog processing using emerging memories, the state dynamics during switching is extremely important to understand the behavior and the mechanism by which we can come up with the physics-based compact model that can leverage and they can facilitate the circuit designers, and then we can come up with the final systems and applications. So I listed just 4 examples where based on different physical mechanisms. So first, charge-based memory, such as 3-terminal synaptic memories, such as a flash memory. Second, the temperature-based memory, such as electrothermal memristors. The third, a mass concentration-based memory, such as diffusive memristor. And the fourth, redox state-based memories such as molecular memristors. So the figure on the left bottom shows one example, which is the charge-based memory, where the trapped charge inside the trapping layer plays a main role, and by which I could come up with a compact model, and then that is readily available for circuit designers. And on the right is exactly what we're proposing as an infrastructure, so that the community of emerging memory can participate and can readily use. So the left one is we named TEMD test bench, which can reveal the temperature-based dynamics, where the state variable is temperature, which is useful for electrothermal memristors. And on the right is a TEM memory extension, which is adequate for exploring diffusive memristor, where the state variable is conduction channel or filaments geometry, such as H or the area, where the mass transport is the main mechanism. But the main problem is for these in situ observation of memory dynamics, especially for nanoscale devices, are challenging experiment. So which is not common in the society yet. So that is the adequate at this moment, very timely for this proposal, and which helps the building the infrastructure across the country. Next slide, please. So yeah, this slide shows what exactly the TEMD test bench does. So on the two plots on the left shows some example publication by which where we use this TEMD test bench. So depending on different current source and the observed voltage across the two electrodes on the memory, we perform the temperature measurement on the device. So the color map shows the temperature information, spatial information ranging from 330 K to 340 K. And then based on that, we could efficiently compact model the electrothermal memristor, which is useful for spiking and action potential of devices. So on top of the existing facility, we're proposing some advanced new system using advanced cameras that is capable of doing even wider temperature sensing range and higher spatial resolution that is adequate for even nanoscale devices, and higher time resolution, much smaller than 10 nanosecond, and even controlled environment, so that we can have some Argon or vacuum environment on top of this measurement system. Next slide, please. And this slide shows another TEM memory extension for mass transport. Again, the example paper is the plot comes from the example paper where Joshua and Changpei did. So depending on the current pulses and voltage pulses, by using this TEM memory extension, which enables users to apply this electrical stimuli while do the high resolution TEM, we could observe the nanoparticle movement, by which the efficient compact model followed by the circuit designer and system level design was enabled. So yeah, that is all for the device level dynamics infrastructure. And the next slide will be covered by Joshua and Changpei about more circuit and system level. Thank you.
Okay.
Changpei, go ahead.
So for the board level testing, we realized when we do the memory for computing applications, there's a need to input, let's say, hundreds of signals at the same time, and also since the current or charge out for like hundreds of channels at the same time, and there's no commercial product for those. So we depending on the input signal, when we do the computing for the physical computing use Ohm's law for multiplication, the input could be encoded with the voltage amplitude, for example, on the upper left. And in this case, we can directly use the Ohm's law for multiplication. We have been using this for a few years, and we developed a prototype measurement system as shown on the lower left. That's 128 by 64 arrays. That's going to be a for as large as 124 by 64 arrays. But on the other hand, if you want to use Ohm's law directly for multiplication, you require extremely good IV linearity, which is not going to happen in the higher resistance range, which we desire, because with if we work with a higher resistance range, we are going to reduce the power consumption largely. So in this case, we will encode the information as the pulse width or the number of pulses, so we can hopefully do the integration of the charge along each column. In this case, the linearity is going to be between the charge and the time. And then the voltage amplitude would be constant. And then the resistance range we can take advantage of is going to be much higher. With this, it's going to be substantially reducing the power consumption for the system. So we also designed a prototype of the board level measurement system, as shown on the lower right. This one is still under testing, but what our plan is, we want to make this available. Number one is we want to expand this to at least 256 by 256 arrays. Number two is we want to bring them up online so the entire community can use it. And then everything would be able to be accessed through your desktop in your office. We are going to be load the chip for you, and then we will have the the GUI interface which you can access from your office. And for the current versions we are building, we put all the proof of circuits, including the digital to analog converters, the trans impedance amplifier, sample and hold, and then also ADCs, et cetera, on the off-chip PCB boards. This surely is going to give us a lot of flexibility, because what you need to develop is really the array with your magic emerging devices. And also there is a plan to put all these proof of circuits on a chip, so we can use a chiplet version. And I believe Joshua has more to say about that, right? Next slide, please, Linda.
Okay, so here I promise this is the last slide. So basically, I'm just going to extend what Changfei mentioned a little bit. For a user, if they want to develop a new type of memory for computing, in-memory computing application, then what they need is a large memory array integrated on CMOS. And then they needed to have the measurement system that is capable of hundreds input, output, analog signal channels, which are not commercially available. And in our center, we are going to help such user to quickly prototype their new memory into large array, and then they can measure it for computing function, for example. So we plan to do that with two approaches. One approach is shown on the left. Basically, we can provide a 1T transistor array, and then let the user deposit their memory on it. Then we have a 1T 1R memory array, and then we can also provide the driving circuit, the PCB version of driving circuit as shown in panel D on the left figure. And then we use a probe card to connect the chip and the driving circuit to do any computing demo you want to do. In this case, you get the flexibility. You can do many different things with different voltage current parameters. But the parasitics is a bit large. So if you wanted to have, this is good for function demo. If you wanted to do a more performance demo, then we have the second approach as shown on the right, which is a chiplet approach. In this approach, we also provide the CMOS 1T array, the user can deposit their memory on it. And the driving circuit, we also provide it's a separate die. Then we can bond these two dies together, use ball bonding or other flip tips, those type of bonding. In this way, it's a more compact integration, and you can get a better performance demo. And from here, you can extend it to a more advanced wafer level of, through silicon via connection or other monolithic integration of memory and CMOS, whatever. So here the center can help the user to prototype and do some preliminary demonstration. I'm going to stop here and,
Yeah.
Linda, yeah.
Thank you, thank you. At this point, as I said, we would like to hear your views. If there is something different that needs to be done, your thoughts in general about an infrastructure of that type, and then its availability. The structure is going to be, our thinking is that it's going to be physically distributed. So hopefully this network can engage others to, if they have unique equipment that can eventually become available to the broader community to connect with the network, because they're going to all be networked for remote access. So at this point, I would like to open it up for any comments, questions. I will keep track of those who want to speak, and we'll start. I mean, we want to hear your thoughts.
And you are also welcome to submit, any comments, questions, either through the chat or send us email later.
So maybe one question that I have, do you agree or have other thoughts of whether such an infrastructure will be of use or important? Yes, Robin.
Oh, you can maybe have that question answered first, but okay, I'll go ahead. So this is Robin Jacobs-Gedrum at Sandia National Laboratories. And I'm wondering if you've considered the development of something like a FOUP that can hold a vacuum or hold a positive pressure argon environment, such that you can transfer samples from one of your centers to another center, kind of allowing your network to be more networked and collaborate and become, share capabilities between the centers.
I can quickly comment on that. That is a great point, Robin. Yeah. So it is not included in our current budget yet, but I guess we can add another chamber and to take samples, from other places which is already protected in vacuum. Yeah. That is a great suggestion. We're going to explore that and to see, how we're going to incorporate something like that.
Thank you.
Yeah, to add on to that, so using the design vacuum chamber to transfer samples is the safest, the best idea. But as an alternative approach, so all different sites has a glove box system, so we can design a package to seal the sample in the glove box, so the sample will only be exposed to inert gases like nitrogen, argon. We can also have a small pump in the glove box to pump the package to apply a little vacuum, and then that package is easier to be mailed throughout the country. So that's an alternative and a cheaper approach, depending on your need.
Yeah. So in our first tool, that is the vacuum level we are thinking is lower than 10⁻⁸. It's somewhere around the 10⁻⁹ tool, because a lot of oxide and those metals can be oxidized, at a vacuum above that. So we wanted to make it as clean as possible. This is not meant to be a tool for production to replace, industry's tool. This is a tool you can think, you can use to quickly solve some of the mysteries in your research and development.
Also, I wanted to go back to this made to show that our goal is, for now, there are 3 locations here, and then the equipment is going to be distributed in those locations, but we are going to network it with National Instruments. It's going to help us do that, at least and then we hope, that shows possible locations of individuals who are doing work in this area. We hope that these will be done in a way that can become available to all of these people from these locations who want to use it, either come to campus or use it long distance, as you mentioned, with the means available to do that. Would I have another question, if I may. Would a network like that, for those who do work in this area, would be useful to you in general?
Right. And if not, why? And if yes, what else we can do to make it better to meet your needs?
This is Deji. I don't know if you can hear me.
Yeah, we can hear you, Deji.
Yes, thank you all, Josh and Zhengfei and Cosme and others for the presentation. I joined a little bit late, but I think this would be a very, very useful infrastructure, especially Joshua, as you mentioned, trying to understand some of this kind of unsolved mysteries that are difficult to do without precise control. So one comment I have in terms of the usefulness is, at least people like me, kind of at the lower level, we work on small scale, devices and materials. We're not making like huge arrays of memory devices. We usually make, much smaller arrays or even single device. So it's not clear to me from the pictures I saw if this infrastructure would be useful for people making, small or single device research.
Yeah, Deji, first, we have the tools to measure individual device, at a controlled environment, different temperature, magnetic field, I believe you have that too. On the other hand, we can also, if, for example, you wanted to make your fantastic memory and scale it up to measure it for a larger array for a computing function, we can provide the CMOS transistor array and then can integrate your film, your memory device on top of that. And not only that, we can help them with the measurement. We have leverage our previous work. We have the PCB level of driving circuit. We also have the integrated CMOS driving circuit. We can integrate such circuit with their 1T, 1R array. The R will, in this case, will be your memory. We integrate them to do a function demo, computing demo. Not only we in the center, we're going to have the hardware, we also have the expertise, people to help with the algorithm and other things for the demo. This is open to everyone in the country who has such need.
Yeah, so with with this kind of
one point here is I believe
Deji, sorry.
Yes.
Sorry, Changfei said he had one point. Can you hear him?
Oh, okay.
Okay,
yes.
so I want to add one point is particular to Deji is for your great stuff. I think Cosme showed a slide that's that certainly is going to work for individual device level. Because you want to comment more on that, the protect environment for 2D materials-based memory devices?
Yeah, so that system is exactly designed for like a device technology with a less maturity level. So we want to integrate all different fabrication, material processing, and characterization tools in the connected glove box system. So the glove box can offer much more flexibility. We can
That's slide number 12. Linda, if you could go there, that's probably going to be helpful.
Yeah, so we are trying to accommodate and design with the users what you are going to need. And then we can design your process together with you and design a flow of experiment, an interactive flow, including the processing and the material categorization and device level categorization. And everything will happen within the same protected environment. So you can better design your interfaces, design your physics, and better understand the memory stiff behavior. We also have a probe station integrated inside.
Okay. Yeah, thank you for this elaboration. So for the 1T1R, the array level, is that 1T going to be provided as a silicon chip, and then researchers can do back end of the line integration of the memory device?
That's
or
the
is
plan.
it a chiplet?
It is a small chip. Yeah, you can, with the vias, and you can integrate your memory on top and to get your 1T1R. That's the plan.
Okay, and then this chip, it will come with a PDK so people can understand the 1T performance on the chip.
Yeah, that will be included. Yeah.
Okay, so we've done this kind of integration. I think for this to be, I think that's a great idea. For it to be useful, that chip has to be planarized at the very top so that it's easy for others to integrate their materials without having to worry about orthography.
Right. Yeah, you're definitely. So you're right there. And then, as in our previous demonstrations, we have shown yet that, that can be done so that's why we're confident this is the available approach.
Great, thank you. There is one more person, Christopher. You wanna go ahead?
Hi, can you hear me?
Yes.
Yeah, I'm Chris Allman from Sandia National Laboratories. I had a follow-up question on that. Where will these silicon chips be fabricated?
This will be provided by the center, and we have different sources to do that. For example, one source could be, in some of the domestic fab, or some commercial fab outside. We have used, outside the country. So we have used both, I would say. Yeah, this is going to be ordered by this center and provide there for you to use.
Okay, thank you.
Right, because we need the pad. We need whatever you do there be compatible with our probe card, for example, with our bonding interface for the driving circuit.
Any other? Let me ask you one more question. Yeah, Jean, go ahead.
Hi. I think this is really exciting. From I guess I'm from JPL, and so we're sort of users of memories, and that I came from the background of developing memories, and so I think this infrastructure is really exciting. And especially in addressing sort of this whole valley of death thing, right? So that where you have an interesting device and you want to be able to see what it's capable of doing. And so I think I have a particular question about your last slide, about your chiplet sort of, stack. So I guess, two things. Has this already been done before? Because what we found, when we were trying to build flip chips and stacks is that a lot of that infrastructure is, at least, for very small geometries does not exist in this country, and things have to be sent out. And that, becomes a problem, and so with export control. And so I was just wondering, if you have any thoughts on that.
Right. Yeah. So very good question. For the one on the left using probe card connection, that has been done and we demonstrated routinely. And for the one, then the other extreme is monolithic integration. Integrate the memory layer monolithically on top of CMOS driving circuit. That has also been done in our recent paper as shown here. Actually, that has been done in trusted foundry in the States. And then for the chiplet, the 1T1R array is one die, then the driving circuit is on the other die. We have not in our group or in this team, I believe we have not demonstrated this exactly that way. And we will do, I guess, depending on the size and the alignment requirement, I know to a certain level, we for sure can do it, but if the requirement alignment is too small, like you said, we needed to explore more places to see where is the best place can get this done. There are still some work
So
need to be
that's
done.
why I need to add to this that yes, this is a 5-year, if NSF of course decides to fund this, they've invited us for the proposal. If they fund it, it's a 5-year program to put it together. Within the 5 years, I know for a fact, at least in the state of Texas at Austin, there is going to be a new facility primarily to do this kind of packaging. And the facility is going to be open to users. And so at least the facility, from what I know, they will start having some tools in line in 2024. So by the time this project is all in one place, or like at least halfway, I believe this other facility will be available for users. And yes, there is going to be primarily a fee to use the facility, but it's going to be a reasonable fee for users. So we don't have to go outside of the US or Europe or Asia, for example. For that, we can do it locally.
That sounds great. You mentioned that this is a 5-year program that's funded. And so do you, I'm just curious as to how do you envision phasing this? Like, what do you think will be available the first year, second year? Do you have sort of a rough estimate?
Plan, yes. So first, we are going to try to do the first demo of networking with existing instruments. And in the process of doing that, we are going to also bring in the new instruments. And so what the plan is, in the first year and a year, practically, is going to be the first demo of the network and existing instrumentation. Then a year and a half, say. Then by 3.5 years within the program, the whole network is going to be placed, because then we need to spend another 1.5 years for the community to run experiments. So we collect data that we will make available to NSF. So it's not like a 5-year program to put the whole thing together, but we will need about 1.5 years for us and the community primarily. This is going to be a community-based, is a user network, right? Obviously. But we will need to make it available then for that period, so the community can run tests, and then we collect data to be able to show how the network works.
Sounds great. We're looking forward to seeing this.
Thank you, Jane. Just wanted to clarify a little bit. This is a proposal, and we will encourage to submit a full proposal after a positive feedback on the preliminary proposal. So we will need your support, your suggestions to make it happen if you feel this is useful for you.
Well, we cannot control the NSF's decision, but we can control the quality of what we are going to submit. And we want to make sure that we, there is a question from Dave Stack on how will users gain access to the network. So the network, there is going to be obviously a web-based system to get access to the network. And it's going to be very similar to what happens, for example, within the AgriFab here, where you have access and then you see what equipment is available, you see which equipment is down for maintenance, for example. We will have redundancy, enough redundancy in the network so people can use, at least in metrology, different types. But then, so there will be fees associated, and that's another effort to develop a fee structure, but it's not a new thing. A lot of universities have developed that, a lot of industry has developed this, so at least we will use our 3 institutions' experience and the process to develop the fee structure, which of course is going to be at different levels, all right? So faculty, individuals from universities will probably get a discounted fee, especially if there are students involved, as opposed to startups, also some discounts in industry. In fact, also NSF will participate in that development of that fee structure on the basis of what goals, NSF has in terms of promoting the workforce development and startups, obviously, for the country.
So Linda, can I make a comment here?
Of course, please.
Regarding the access, especially particular for the testers, we had enough experience for remote control. Even when we were doing the array level of testings, the students always want to load the chip and operate everything from another room, because we want to minimize, when we have the Pro Card version, we want to minimize the perturbation to the system, including if you walk, there would be vibration, right? That kind of factors. So we always load the chip, leave the room, and go either to the office or they even go home and operate the system and do all this fancy work from another computer. And there is IT support with this. When this is online, we can use that model to, you can send us your chip, we load it, and then you can, either you are in Arizona or Florida or Texas, wherever you're going to be, operating the system like in your lab.
Oh yeah, Chiang-Fei, I have to tell you, my student is working on your system from here. He's running.
Yes.
You have to know that. Yeah, from and the question about iLab. So National Instruments has a system level software which can incorporate heterogeneous softwares. So because iLab is utilized here in AgriFab, but other institutions may have different ones. And that, that happens with industry too. So they have the capability to incorporate in one network heterogeneous systems in terms of the network softwares that they have, local network software. Well, we are at 12 o'clock. We want to honor our promise that it's going to take an hour. However, what I wanted to show you is that the next steps will be the following. We are going to just make a short summary of suggestions, and we'll make the recording also available to all of you. There are individuals who have registered who could not participate and asked us for that. And then so we are going to create a webinar page to have it available for you, but also any other comments you may have, any other suggestions, please forward them to us. And will be our emails will be available on the website. Anything you have that you think is gonna be important to know for this network will be very important to us. So thank you so much again. And I want to thank all of the speakers and all of you for being with us for an hour.
Thank you very much. So, if you feel this is good for you, you can send us emails. You would be happy to support to provide a supporting letter. We can send you a sample letter so that once this is ready, then it can benefit your research and development. And this is also for workforce development to educate students in the critical in-memory computing domain. Yeah. Thank you.
So much. Thank you.
Thank you.
Yeah, bye.
Thank you. Bye.
Okay, Yunzhi, do you have any question or comments? Yunzhi? Okay. I guess he's probably not, yeah. Yeah,
So
Yunzhi is from Argonne National Lab.
yeah, perfect. Well, we can talk about this. I think we did not hear any objections, at least. Some
I can feel the excitement, yeah, and this can help people, yeah.
few good suggestions. So we'll find some time to meet on Sunday
Okay,
to go over some of these things. Perfect.
great.
And I was thinking, one more thing, that it will be good to use, since you put these nice presentations together, maybe we can use those in the supplemental funds in front of the various instruments.
Yeah.
Whatever we can do to help, people understand what we're trying to do is going to be useful.
Right. I also have a screenshot of all the attendees.
Okay, perfect.
Yeah.
All right, excellent. So we'll talk on Sunday.
Okay, great.
Perfect.
Thank you, Linda, for organizing this.
Absolutely.
Thank you.
Yeah.
Thank you.
Bye.
Bye-bye.
Mhm.
Bye.